Okay. The next item I'm going to present is what's known as micromechanics. Micromechanics. All right. Does anyone know what micromechanics is? Have you heard of it? Yes. There are a few people. Okay. I'm not guaranteeing you'll have better idea after this, but I will try. Okay. So, what is micromechanics? So, micromechanics is it's a process of combining the mechanical properties of different items to get the mechanical properties of the composite. So if you have 3 or 4 constituents like fiber, different types of fibers, different types of matrix, of course only one type, then the matrix has one set of mechanical properties. The fibers will have a different set of mechanical properties. So the mechanical properties of the composite will not be same as fibers, or they are not going to be same as that of the matrix. So how do we combine those two sets of mechanical properties to get the composite mechanical properties? That's what I'm trying to explain. We won't have much time to explain this, so I will show you a few items, just a few items that are very important to us initially, and then I will give you my notes. I will that has everything else. Okay, so we are already behind by one session, so I'll try to go a little bit faster. So obviously when you have fiber and matrix, there are two different materials, but when we are working with composites, we will work with only one set of mechanical properties. Therefore, we need to work with only one set of properties. And that's what we are going to do in this micromechanics. And also you can actually design, I don't know, I'm again putting you on the spot, don't mind, but what's the amount of fiber you have in this? Do you know? No, I'm not talking about the price, volume fraction. 70%. Yeah, 70 sounds a bit high, but 50 is more likely. But anyway, so it's maybe about 50 to 60%. What about that one? Maybe about the same. Yeah. So, okay, we'll talk about it in a minute. So, if you want to just, it's always useful to increase the volume of fiber. More the fiber volume, more the mechanical properties that will be similar to fiber properties. Does it make sense? So, if you have larger amount of fiber, you will have mechanical properties of the composite that are more similar to the mechanical properties of the fiber. But if you have very small amount of fiber, let's say 5% by volume, I am assuming it's by volume. If it is by weight, it's different. By weight, okay, that's the reason you are saying 70%, okay. Anyway, so if you are just using 5% by volume, so imagine only 5% of the total volume is fiber, 95% is matrix. Therefore, the property of the combined system will represent only 5% of fiber properties and 95% of matrix properties. However, we would like to maximize the amount of fiber in the cross section, so we would gain strength. Does that make sense? But you can go only up to a certain amount, because typically 50 to 55% is considered to be, by volume, is considered to be normal. 60% is slightly high volume. But definitely industry is trying to increase the amount of fiber, because you improve your properties and make it very similar to fiber properties. Fiber is very, very strong. Matrix not so strong, right? We know that from yesterday. So, in some cases, may not be in rebar, but in other cases, you may just need 10% fiber as opposed to 60% fiber, right? So if you change the fiber amount, the properties will also change. So you can design your component based on the requirements, based on the amount of stresses you need to carry in your composite, and therefore we can use micromechanics to do that kind of design. Does it make sense? That's the basis for micromechanics. Is this clear to all of you?
Yes, sir.
Very good. So if you cut a cross section through a composite and look under magnified, under very high magnification, you will see the fibers are dispersed throughout and there is matrix, right? So, and do you see anything else in this slide?
Cross section.
Yeah.
Not uniform. Fiber cross section is not uniform.
Perfect. The diameter of the fiber is not uniform. You will see the diameter varies substantially. But we cannot consider that. We always consider average diameter and amount of fiber based on the total fiber, and we'll always work with weights rather than volumes. I will talk about it in a minute. So this is a typical cross section. How do I design for this? So that's what we are going to learn now. So if this is a plate, imaginary plate, it's not real because you cannot have plate thickness which is accommodating just one fiber in each layer. That's impossible because it will be such a small layer. So if you imagine this plate to have one layer of fiber, rest of it is matrix. In the direction of the fiber is longitudinal direction. That's what we will call this. Longitudinal direction refers to the direction parallel to the fiber. In this system, global system, it's number 1, and this is 2, and that's 3. In most cases, we will not have, or number 3 is not likely to govern our design. In most flat structures, like this one here. So this is a flat plate, right? Almost flat plate. The third dimension properties are not as important as the properties in plane. And in plane we have two directions. One is longitudinal direction and the other one is transverse direction. The third direction is this one here, perpendicular to the plane 1, 2. So you'll have in any plate, this plate here, we can call this a layer, you can call this a ply, or you call this composite, people like to call it lamina. So we will have many fiber layers. They are not perfectly arranged the way it is shown here, not in a rectangular pattern, but let's assume that they are appearing like this in regular pattern. So if you have a composite, you cut a slice through the composite in the perpendicular to the fibers, you will see fiber cross section right here. These are all fibers. Rest of it is matrix. If I apply a total force in this direction parallel to the fiber, okay, some of the force is carried by the fibers and rest of the force is carried by the matrix. Okay, so we'll try to find out how much of the force is carried by the matrix, how much of the force is carried by the fiber. That's one of the things we will do. So that way you can actually design your thickness, design the amount of your fiber, volume fraction, and things like that. Once again, as structural engineers, you and I may not design that. We will leave it to the supplier to give us all the information related to these properties. That's what we will rely on. So micromechanics is a process by which you have heterogeneous arrangement and material properties. As input, we get this as our basis, and then we will come up with material properties that will not distinguish between fiber and matrix. Okay, that's what is micromechanics. So we are now eliminating the consideration of fiber and matrix separately, and we will come up with mechanical properties that represent the composite as a whole. So in this case, we have what's known as RVE, which is representative volume element, RVE. So here it's just for theory, okay, just for derivation of equations we'll use this. So in a composite, it doesn't matter how many fibers you have. If they are uniformly distributed, let's assume they are uniformly distributed, each fiber is associated with a small amount of matrix. So if I consider just one fiber or one unit of the fiber and the corresponding matrix surrounding this will give me same properties in terms of stress compared to a large or larger composite section, cross section with multiple fibers and larger amount of matrix. That's the definition of RVE, representative volume element. Okay, so they say there are different packings possible, rectangular packing and hexagonal packing. That's what they say. I really don't know how we can differentiate between the two, but in any case, for mechanics we will just consider one unit of fiber with the corresponding matrix, and if I deal with that and get all the mechanical properties corresponding to this in terms of stress units, the entire composite can be represented with similar properties. Okay, so we'll just try to use this concept where we have fiber here, matrix on both sides. Just to make it symmetric, they arrange matrix half of that here, half here, and then when you apply load, depending on the type of load you have, there can be Poisson's effect, that means transverse shrinking of the composite. So this is length L, the elongation is delta L. So we will deal with stresses and strains, very simple stuff. It's all mechanics of materials level equations, very simple equations. So if you have a known set of properties for fiber and for matrix, those are obviously heterogeneous materials, two different types of materials. We will convert it to uniform material without differentiating between fibers and matrix. Okay, so obviously the conversion will depend on matrix properties and fiber properties, of course the geometry of the microstructure. For these derivations we will use, from now on I will just bear with me, we will deal with mechanics just for a little while, in which case we will use all these equations with some of the notation that I am going to use here. So if you have an isotropic material that has properties in same properties in all directions, that's isotropic material. All that you need is two constants. One is E and the other one is Poisson's ratio nu, right? So modulus of elasticity and Poisson's ratio will define all the mechanical properties needed if the material is isotropic in nature. However, if you have anisotropic material that has different properties in different directions, you will need as many as 21 properties to define the complete state of stress in the material. Okay, so that's the big difference between two constants, which we are quite used to using. Two constants, we use shear modulus equals modulus of elasticity over 1 plus nu. These are things that we are used to, but in case of materials with different properties in different directions, we need to probably have as many as 21 properties. So what's my notation? I will use volume of composite material, that is, if you are using a unit composite, if you are considering 1 unit of the composite material, that volume is lowercase v. That's a lowercase v, not uppercase, not capital V, just small v. Lowercase v. Volume of the fiber, V sub f, this is V sub c, and for matrix it is V sub m. So that's the volume. In case of weight, we will use W for weight, lowercase w, which is small letter, not capital letter. W sub c, W sub f, W sub m, 3 different weights. What about densities? Densities will become important just for batching, very important. If you are fabricating a composite, you will need that densities, rho c, rho f, and rho m. These are the 3 different densities. Okay. So for actual mechanics calculations and stuff like that, volumes are convenient. So if you can, it's convenient to work with volumes when you are doing your mechanics of the composite. However, if you are batching, if you are fabricating a composite, you really want weight batching, because volume batching, how will you measure the volume of fiber, right? I mean, you can, it's not that you cannot, but it's more convenient to weight and work with weights. It does make sense? So for actual analysis, we like to work with volumes. So what we will do is we'll convert weights to volumes if needed. And when you are fabricating, you will need, it's more convenient to work with weights. And therefore, we will, if needed, where needed, we will convert volumes to weights. So we should be able to work with both volumes and weights, which we can. It's very simple. So we will, in our equations, we will use a few definitions. We will define fiber volume fraction. Fiber volume fraction, V sub f, as volume of the fiber over volume of the composite. So the whole composite volume is V sub c, that includes fibers and matrix, and V sub f is only the volume of the fiber. Okay, so that's the definition of volume fraction. It's important. These definitions we will use in our calculations. What about matrix volume fraction? Same approach. Matrix volume fraction, V sub m equals Vm, V sub m over V sub c. So this is an uppercase V. So don't get confused. This is also an uppercase, the capital V, uppercase V, and this is a lowercase v, which is small letter. So the volume of the fiber plus volume of the matrix equals total volume, which is equal to V sub c. Okay, so V sub c, lowercase, V sub c equals Vf plus Vm. And volume fraction, you will see volume fraction is defined as V sub f over V sub c. Matrix volume fraction is defined as V sub m over V sub c. So V sub f plus V sub m equals 1. That's the advantage of using fractions rather than absolute volumes. So from our basic knowledge, we know weight equals density times volume. So we will use those notations. We say V sub c equals Wc over rho c, V sub f equals Wf over rho f, Vm equals Wm over rho m. Very simple. So fiber weight fraction, that's another definition. So just like our volume fraction, we will use volume fraction in our design analysis. We will use our weight fractions in our actual batching, fabrication, and processes. So weight fraction, fiber weight fraction is W, uppercase, which is capital letter. Wf equals lowercase, which is small w subscript f over w subscript c. So once again, wc plus equals wf plus wm. Okay, so of course matrix weight fraction is wm. Okay, so based on this, assuming that there is no weight loss during the actual fabrication of the composite, we have wc, which is the weight of the composite, equals wf plus wm. W is nothing but density times volume. So plug in those numbers. So if you plug in those numbers, you'll see rho c vc equals rho f vf plus rho m vm. This is based on the weights. Now if I'm interested in finding out the density of a composite with certain amount of fiber and remaining amount of matrix, I can just rearrange these terms and say rho c equals rho f times vf over vc plus rho m vm over vc. So this is nothing but, by definition, vf over vc, fiber volume fraction, and vm over vc is by definition matrix volume fraction. So now we have rho c equals rho f vf plus rho m vm. So what you see here is we can calculate the density of the composite based on the proportional amounts of fiber and matrix. So when you are working with your composite, you will know the density of the fiber. They will give you a specific gravity. Let's say for basalt it's 2.5 or something like that. For glass it's probably around 2.2 or something like that. So fiber density is known, matrix density is also known. Matrix may be 1.2, something like that, depending on the type of matrix. So you know the density of the matrix, you know the density of the fiber. Depending on the